This we will study about pulse NMR. It is also Fourier transform in NMR. All recent NMR instruments are based on pulsed or FT NMR. Let us see now. It is very easy to understand. In continuous wave NMR, it is the old version, and RF radiation is used to affect a radio frequency radiation is used to affect the nuclear spin transitions. Similarly, in EPR, microwave radiation is used to cause the electron spin transitions from ms minus off to ms plus off. We have studied earlier. Here, RF radio frequency radiation is used in pulse NMR. The radio frequency radiation is used in the form of short, quick pulse. Flash pulse is nothing but a flash of RF radiation. The principles of pulsed NMR and EPR are also very similar. In EPR, microwave radiation pulse is used, whereas in NMR, radio frequency radiation pulse is used. The advantage of NMR is that the advantage of pulsed NMR is that NMR measurements is completed in seconds, less than seconds, whereas in the case of continuous wave NMR spectrometer in older version, the time it is time consuming. We'll see further. As I explained earlier, the continuous wave NMR, it is the old version of NMR instrument. It is time consuming. We need to take several scans. It will take long time for recording, measuring NMR spectra of for a single compound. If the intensity is very low, then we need to carry out several scans. Whereas in modern pulse NMR, the sample is excited by a single multiple pulses of strong radio frequency wave of range of frequencies. Then the free induction decay is picked up on a receiver. We'll see the NMR measurement is completed in seconds. This is very important. It is time consuming, the continuous wave NMR, whereas pulse NMR, the scanning, the measurement is completed in a few seconds because we use NMR radio wave pulse of a range of frequencies. We'll see the principles of it in the slide. To understand the pulse NMR or pulse EPR, we need to know the what is magnetization, what is net magnetization. Let us consider electron spins, either in clockwise spin or anti-clockwise spin. They are degenerate in the absence of magnetic field. They are all randomly oriented in the absence of magnetic field. When in the presence of magnetic field, V naught, these electron spins or nuclear spins are oriented. For example, Mi equal to plus of is oriented in the direction of the field. They are lower in energy. Mi equal to plus of is lower in energy. Therefore, the it is more populated, more number of spins in the ground state. It is the anti-clockwise spin. Anti-clockwise spin, Mi equal to minus of. It is the excited state. The number of spins with Mi equal to minus 1 by 2 is less. The population is higher in the ground state. Therefore, on subtracting, uh, we will get the net magnetization. Overall magnetization is in the Z direction. At equilibrium, the overall net magnetization M naught is in the Z direction. The net magnetization is shown here. The net magnetization as shown here, the previous slide here. Okay, it is in the Z direction. It is in the Z direction. When you apply a when you apply a 90-degree pulse, you apply a 90-degree pulse, that is pi by 2 pulse. That is when you apply rotating magnetic field, radio frequency field, perpendicular to the z-axis, that is through x-axis. It is tilted. The magnetic, when you apply the pulse, radio frequency oscillating magnetic field, it is tilted along minus y-axis. This is plus y-axis. It is tilted along. Therefore, the the two levels are equally populated. The two levels are, when you applying the 90-degree pulse, the two energy states are equally populated. They are saturated. Now, when you apply 180-degree pulse, pi pulse, the net magnetization is tilted opposite, that is plus z-axis to minus z-axis. In this case, there is a population inversion. You see, this is thermal equilibrium. The net magnetization is along the z-axis. On applying 180-degree pulse, the magnetization is tilted opposite to plus z. It is in the minus z-axis, minus m naught. There is a population inversion. Now, what is pulse angle? This formula is very, very important, asked in CSAR and GATE. Problems were asked based on this. What is pulse angle? This is the angle through which the net magnetization is tilted from the z-axis. For example, 90-degree pulse. This 90-degree pulse, and this is 180-degree pulse. Theta equal to 180-degree pulse. Theta is radians. It is directly proportional to the rotating, oscillating radio frequency field, magnetic field. It is applied along the x-axis. It is the pulse. It is the oscillating, rotating magnetic radio frequency pulse. V1. It will be given. And what is TP? TP is the length of the time of the pulse applied. How long the pulse is applied. For example, if you apply for long time, then it will be tilted to minus z-axis. If you if you give if the length of the time of the pulse is very less, then it will be tilted by a 20-degree, 10-degree, etc. Therefore, the pulse angle depends on the applied radio frequency pulse and magnetic field, and also on the length of the time of the pulse. What is population inversion? On applying 180-degree pulse, pi pulse, when the pulse angle is 180-degree, the net magnetization is tilted from plus z to minus z axis. At that time, the population of excited state and ground state are reversed. It is called population inversion. Whereas when you apply pi by 2 pulse, 90-degree pulse, the energy levels are saturated. There will be no signal. Here we will see there are two important phenomena in pulse NMR or pulse EPR: free induction decay, FID, and spin echo. These are all very important in ESR, pulse NMR spectroscopy, or pulse EPR spectroscopy. This is again a very simple if you understand pi by 2 pulse, for example, when you when you give pi by 2 RF radio frequency pulse, okay, what will happen? I have shown here pi by 2, and the detector, when your eye is in the minus y axis, when your eye is in the minus y axis, okay, now the magnetization is very high. As you see, the magnetization is initially very high in the detector, okay, so it is very high. After some time, after with increasing time, the magnetization, the individual magnetization fan out. Therefore, the intensity decreases. The intensity of the FID decreases, and finally it will reach the equilibrium net magnetization. It will go to Z direction. Therefore, the FID signal, free induction signal, is decreasing with respect to time, because the net magnetization uh, along minus y axis undergoes precision, and it fans out, therefore it decreases. Now let us see, once after pi by 2 pulse, now they, after it comes back to equilibrium, thermal equilibrium position, net magnetization is along the Z direction. The pi pulse is now applied. The pi pulse is now applied, as you see here. Okay. Now the when you observe along minus y axis, there will be no magnetization, because the magnetization is now along minus z axis. There is no magnetization along minus y axis, therefore it is zero. And with increasing time, the net the magnetization fans out, and therefore the signal increases and then decreases because of this phenomena. This type of signal obtained is called spin echo, and this signal is called free induction decay, because the signal is decreasing with respect to. This is the free FID signal along the transverse magnetization my with respect to time, magnetization along the y axis, as y axis, it decreases with the increase in time. We have seen earlier. On Fourier transformation, an absorption signal is obtained. However, if the magnetization is observed, the magnetization, or if the detector is in the x-axis, there will be less signal in the beginning. With the increasing time, the signal decreases, because the net magnet, after applying pi by 2 pulse, the net magnetization is along the y-axis. The magnetization is intensity is very large. The magnetization along my, after time, it will be decreasing. Here, since it is along the my axis, mx will be 0. With increasing time, it is increasing and then decreasing. On Fourier transformation, dispersion the dispersion spectrum is obtained. Let us see now what is time domain NMR spectrum or ESR spectrum, frequency domain ESR spectrum, NMR spectrum. Now the magnetization, this is the free induction decay signal, FID signal. This the magnetization along the my axis. The magnetization along Z axis is called longitudinal magnetization. This is a transverse magnetization. along x-axis, y-axis, the magnetization along x-axis, y-axis are called transverse magnetization. It decreases with respect to time. This is this FID signal is called time domain NMR spectrum. This does not give any useful parameters. However, on Fourier transformation, a mathematical process, even our eye does Fourier transformation to give the image we can see because of Fourier transformation. This is a fundamental mathematics. We don't know, but our eyes are doing this even for uneducated. They don't know. He doesn't know mathematics. On Fourier transformation of FID signal, here you will get one signal because you have only one proton in the compound. Suppose you have two different types of protons or three different types of protons. The FID signal will be, the nature of FID signal will be different. It will be comprising of two different types of protons. You have two different types of protons. Of it. Fourier transformation, you will get two peaks. Means there are two different types of protons with the different chemical shift values. In this, let us see what are relaxation processes and times. So here at equilibrium, the ground state is more populated. The ground state is more populated, and the excited states are less populated at particular applied field strength. For example, V naught. On irradiation, for example, on applying the pulse on irradiation with the radio frequency oscillating field, now the population is inverted. On irradiation, more the excited state is more populated than the ground state. Therefore, there will be no absorption once the excited states are more. There will be absorption of RF radiation as long as there will be population difference between the ground state and excited state. Now, in this state, there will be no NMR absorption, but due to relaxation process, there are two types of relaxation process. We'll see T1, T2, and they come back to the equilibrium levels. There are two types of relaxation process and relaxation times. One is spin lattice longitudinal relaxation process, long time. Spin relaxation process, spin relaxation time is given by spin relaxation time. Now let us see what is uh, spin lattice relaxation. It is represented by T1. The excess energy, as we see, the excess energy is transmitted to the surrounding. In the case of spin lattice relaxation, the excess energy of the spins in the excited state are transferred to the lattice vibrations. Lattice vibrations. Thereby, it comes back to its thermal equilibrium position. Okay. What is the T2? T2 is spin relaxation time. It is represented by T2. It occurs due to the direct interaction between the two spin states. Two spin. For example, one spin interacts with the neighboring spin. As a result of the spin interaction, there will be the energy is transferred from the excess energy is transferred from the excited state to the neighboring spin state. Now we'll see how the relaxation times are measured. They are very, very important because usually T1 is great, spin lattice relaxation time is greater than T2. Okay, spin time. If relaxation is fast, If the relaxation is very fast, NMR spectrum will be very broad. You won't get NMR spectrum. Problem. So it is a it is a physical kind of problem. But if the relaxation time is short, for example, in the case of EPR, the relaxation time is very short. It is because of that, NMR ESR lines are very broad. We have seen earlier. That's why the derivative signal is measured. We will see further. As a consequence of T1 and T2, if the relaxation times are so fast, then J coupling also not resolved. Therefore, the structure of the structure could not be elucidated using NMR if T1 and T2 are short. The relaxation here, how T2 T2 is nothing but spin relaxation time. How it is obtained? Spin relaxation time is obtained from free index and decay. We have seen it is very simple. We have already seen the free index and decay. It is obtained from FID decay, free index and decay. T2 is a measure of the decay of the transverse magnetization called transverse relaxation time. It is also called spin relaxation time. Is also called T2 is called transverse relaxation time. Transverse because of the transverse relaxation process. For example, here on applying pi by 2 pulse, the magnetization is tilted to, as you see, the magnetization is tilted to x-axis to minus y-axis. Therefore, the magnetization is now in the y, m of y, mz. In the z-axis, it is mz. The net magnetization equilibrium is on applying pi by 2 or a pulse tilted to minus y, transverse magnetization. Now the decay, because the individual spins resist, fans out, then the magnetization along my, this magnetization along my decreases with respect to time. Okay, with respect to time. Therefore, the magnetization my or mx my magnetization is decreasing. This is the initial magnetization m naught and d equal to 0. Immediately applying the pi by 2 pulse, that is equal to m naught. With the increase in time, as you see, the signal decay, the signal decay, that is called free index. And by fitting the curve, you know, using this equation, by fitting the curve, my is known. It is measured by using detector. M0 is known. It is also detector can be detected. And e power minus t by t2, t is the time, the magnetization of my. Therefore, using the by fitting the curve, by knowing the my, m naught, and time, we can calculate the transverse relaxation time or spin relaxation. In this, we'll see how T1 is measured. It is measured spin lattice relaxation time, also called longitudinal relaxation time. It is measured using saturation recovery. It is very simple. What is saturation recovery? If you look at here, on applying 90-degree pulse, the net magnetization is flipped to y axis. Now, in this case, in saturation recovery, your eye is in along the z axis. Okay, as you see, in the beginning there is zero magnetization along z-axis because we have applied pi by 2 pulse. After some time, with respect to time, the magnetization returns to, and finally, after certain time, it will reach the equilibrium value. The net magnetization will be back to plus z axis. Therefore, T1 measures the return of the Z component of the longitudinal magnetization MZ to its equilibrium value. This is called saturation recovery. Okay. Let us see now, as you see here, M0 at this time, immediately after applying the 5 by 2 pulse, there is no magnetization along Z axis. This is M of Z, and there is no magnetization at time t equal to 0. With increasing time, there is a return of Z component. The Z component in the individual nuclei returns to the equilibrium position due to the because of and it fans out. It, it is in the case of saturation recovery, the return of the net magnetization back to the plus Z axis is followed. Now, by fitting the curve, this curve is obtained because m of z equal to m of 0, 1 minus e power minus t by t1. In this case, m of z is measured using this placed along z axis. Okay. Now m0 is in initial magnetization at equilibrium, and with respect to time, the net magnetization increases. Is it because of the return of the Z component of the longitudinal, the XY transverse, whereas Z is the longitudinal magnetization component, equilibrium value. By fitting the curve, we can calculate the T1 value by using saturation